Good morning. It was an absolute thrill and honor to be invited to give this address to this conference. Um, as you can probably tell, I did not grow up in America. And so in looking at this, I did a bit of research into the American customs. And I believe for a State of the Union, I should begin as follows. Caregivers, families, colleagues, friends, the State of the Union is strong. But it is strong. Well, to me, the journey in SCN2A started in 2012. It was just some characters I saw on a computer screen. As Leah was saying, the idea that we'd be here now, this year time, with so many people, so many working together. We have clinicians, scientists, caregivers, all pulling together. And it really is a phenomenal thing to see. Today, I'd like to give an introduction to some of the important parts of that journey in SCN2A. I'm going to start, is that going to go forwards? There we go. Just with my disclosures, these are the individuals and groups that I receive funding from, including Biomarin Pharmaceuticals, a lot of it thinking towards therapies and rare genetic disorders. Oh, there we go, a little bit eager there. So let's start off with why this all began in 2012. This is a timeline of understanding rare genetic disorders. Begins in about 1980s. Improvements in being able to look at genetic data allowed people to start identifying genes underlying disorders. But it only happened in a very small number of disorders. It was ones which were clinically identifiable, like cystic fibrosis or Dravet syndrome. So these disorders got something of a 30 to 40-year head start because the genes were identified a long time ago. But the energy of this started to run out, and there was quite a long period, especially for brain-related disorders, where there really wasn't very much progress at all. But that really changed with the sequencing of the human genome, which is in about 2000, and then with the development of exome sequencing technology, which I expect many, many families here have gone through, and that's how the diagnosis was made. And it was from this which led to the recognition of SCN2A as being important in epilepsy, autism, and developmental delay. But it wasn't just SCN2A. This was allowing to look at many, many syndromes which didn't stand out clinically. And so on the next slide, I'm going to show you a picture of all of the syndromes which have been identified in that 10-year period. So here we go. And you can see it's not just SCN2A. There's over 300 different genetic disorders here. The size of the circle relates to the number of individuals who've been identified for each one. And there, at number 4, is SCN2A. And we can do the same if we look at epilepsy. So there's many, many genes have been associated with childhood epilepsies. And there, at number 3, is SCN2A. And I show you this for 2 reasons. Firstly, SCN2A is one of many, many disorders here. And each one together is embarking on a similar quest. And so each family is not alone, we're part of a community of SCN2A, but even SCN2A is not alone, it's part of a wider family of developmental disorders. And with advances in genetic technologies, actually the route towards therapy is very similar for all of those together. And so while we may feel rare, we are part of a much, much, much wider group. And the second thing is, within that, SCN2A is one of the more frequently observed genetic disorders. So that means that as companies start thinking about where therapy is going to be done, SCN2A rightfully should be towards the top of that list. So what is SCN2A? So SCN2A is a gene which encodes a protein which we call NAV1.2. On the left is a simple example of this. It's made up of about 6,000 building blocks called amino acids. For context, that's about the same number of pieces as in the Hogwarts castle made by Lego. And the purpose of all of that is to create a channel which lets sodium through in response to a change in voltage. So you can see a simple schematic on the left, and that's the one we're going to use the rest of the slides. On the right, you can see the actual structure. If we were able to zoom in enough, it's so small, you can't just look at it through a microscope. But if we use methods to look at the structure, that's what it looks like on the right. And you can see the line in purple, and that's where sodium goes, sodium as in common salt. And we're going to see what a fundamentally important role that plays in a second. Or not. Oh, okay. So here's a picture of a neuron shown on the left here. This is a single neuron in a brain. Inside each one of our brains, there are 100 billion neurons looking like this. Inside those, you will find this channel, NAV 1.2, and there'll be thousands of copies of it there. So just to give an idea of the scope of the challenge here, there are literally trillions of these channels in our brain. In its normal state, it sits there closed, but it performs a very important role. When it opens up, it allows sodium to go rushing into the neuron. This creates a spike, which is called an action potential. And that action potential is how neurons talk to each other. It then closes, allowing potassium to go in to restore the voltage, and then the entire thing resets. So this forms such a fundamental process that sitting here now, all of you will have been using this channel, SCN2A, simply to listen to and possibly learn from something in this talk. So when we start thinking about SCN2A variants leading to problems, we've identified as a group several different patterns by which this can happen. So here we're going to show the spectrum of SCN2A related disorders. In the middle, we have an example of that channel in the normal state, letting through the normal amount of sodium. On the right, we have a group of individuals where less sodium is allowed in. So this is called a loss of function, and we see a reduction in sodium. This tends to present with developmental delay or autism, and seizures might be a component, but they tend to come on later, after 18 months or maybe after a few years. And as a group, we think this is the largest group out there, though many of these children are undiagnosed because genetic testing is not so routine in autism and developmental delay. On the other extreme, we have developmental epileptic encephalopathy. So this is characterized by very early onset seizures, sometimes on the first day of life or in the first few months of life, sometimes even before birth. And here it's the opposite problem. Too much sodium is coming in, and this makes the neurons hyperexcitable, as in they react too easily, which you can see how that would lead to seizures. Between those, we think there is a milder group. This is slightly less well characterized, but this, when we have a milder gain of function, this leads to symptoms like episodes of being unbalanced and maybe mild developmental problems. And then for completeness, there's also a group who have benign infantile seizures. This often runs in families, and I doubt that this is represented here at the conference because it largely resolves within the first year and should lead to no long-term problems. Now, there's one other group to add to this, and that there's a group who have mixed gain and loss of function. And I think it's fair to say that this is the area where, as scientists, we're working the most to try and understand exactly how this fits in. Now, I've presented this in a simple way of there being too much sodium or too little sodium. And so I can see in that model, it doesn't really make sense that you can have both together. But let me try to give an example of that. You might have a situation where the channel doesn't like opening. And so it takes more membrane potential change to actually open the channel. And so that's a loss of function because it's making it harder for the sodium to go through. But when it opens, it stays open. So that leads to more sodium coming through, and that would be a gain of function. And so it's that group there tend to present with seizures sometime between 6 and 18 months, usually associated with developmental delay, and sometimes with a movement disorder. And I think it's fair to say that we're seeing a very complicated relationship between how these individual Lego blocks, which are changing the channel, lead to symptoms. And I think that's more true in SCN2A than most disorders, meaning there's even more importance to that scientific endeavor of understanding it. So why does this all matter? Well, it really comes down to therapy. In the simplest way, if we can apply this model, if we take the loss of function end, our objective is to increase the amount of SCN2A or increase the amount of sodium being moved. On the gain of function end, our objective is to do the opposite, to decrease the amount and decrease the amount of sodium going through. The mixed presents more of a challenge. There, we can't simply increase it or decrease it because it is a mixture of both. What needs to be done instead is to reduce the bad copy. And so we'd call that an allele-specific therapy, or to edit that variant back to the normal sequence. Now, if we were able to do that, that would probably also be a beneficial therapy in the pure gain of function end as well. And so the reason we focus on this loss of function, gain of function, and mixed is because it's directly relevant to the therapies which need to be created. We have seen immense progress take place in SCN2A. The gene was first identified in the late 1980s, but then it took another sort of 10, 15 years or so before it was first associated with benign seizures. You can see on the right, and that's sort of shown at the 2000, that there was a big increase in the number of publications there once it was recognized that it had a role in human disorders. Then around 2010 and then 2012, the relationship between early onset seizures and between autism became apparent. And that's led to an even greater interest in this. And you can see the publication numbers are going up and up and up. Amazingly, within that time, we already start to see some progress in the therapeutics. And in the space of medical science, that is a quick time to get to therapeutics. We've also seen landmark moments within the group. For example, the founding of families SCN2A, which is why we're all here today. And I think it's fair to say, as a researcher, we've seen the impact of the RARES1 and TASCO have a dramatic effect on just really bringing everything together and moving it forward. Come on, there we go. We have an incredible group of people who are genuinely working together. The family group, the scientists, the clinicians are regularly in touch. It's not just meeting up once a year. There are regular emails, regular discussions going on, and really are united as a group towards these common goals of getting there. We're having success in raising funds, in holding conferences and publishing papers, all the metrics of making progress. Most importantly, the number of people being brought into this community is going up and up. But there are still many things which need to be achieved. And I've identified here the 5 major tasks we need to be able to perform. Firstly, there's important roles of understanding the biology. In all of those, the gain of function, the loss of function, and the mixed. This is best done in big labs, in scientific labs, trying to make sense of this, and there's progress which is happening, but we need to make a lot more progress to fully understand how these variants lead to symptoms. A major part of that is characterizing what each of the variants does. Back to my Lego analogy, we need to understand what happens when you remove Dobby's head, take off the top of the castle. Each one of those variants needs to be understood. As we start thinking more and more about therapy, we're going to have to ask an important question: what do we measure in a clinical trial? And that's why these endpoints are so critically important. So I would urge everyone here to participate in that dragonfly study. It really is critical to get towards therapy. We have the important piece here of identifying biomarkers. So this is a picture of my dear friend Kevin Bender and his new gear for testing eye movements. This is a reminder to ask everyone here if it's appropriate to go and sign up for those biomarker studies, the eye movements, the EEGs, the video matching. All of that is really, really important. Kevin has asked me to put in a particular request for children who are siblings without symptoms or children on the loss of function end to go and visit for the eye tracking movement, even if you don't have an appointment. At the back of here, you'll also find QR codes where you can sign up and contact them directly. All of those groups are very, very, very keen to have people participating, and it is critical for our progress. And then lastly, we have the important piece of developing therapies, and that's where I'd just like to end here. When we start thinking of what a therapy would look like, I would think of it in three major groups. The first group is about small molecules. These are the kind of pills which we're all used to taking day to day, but of course then specific to these disorders. These would be pills taken by mouth, maybe once a day, twice a day. And we expect these to be relatively safe because it's a tried and tested regulatory pathway. Critically, if it isn't safe, it can be stopped and you expect the symptoms to go away quite quickly. In the middle, we have a genetic therapy. It's like a genetic therapy light called an antisense oligonucleotide. These are completely specific to SCN2A, but then they are given by being injected into the spine maybe every 3 to 4 months. This is a relatively new class of medicine. As a result, less is known about how to make it perfectly safe. And so there's a degree of concern about the safety profile for these, but there's an emerging regulatory path. And there's also the advantage that if it doesn't work properly, it can be reversed, albeit with a 3-month wait. And then on the far right, we have therapies delivered by what would be called vectors, maybe viruses or nanoparticles. These would be given as a single dose, maybe into the blood or the spine or the brain. And it would, in theory, be a single dose, which was the therapy forever. Right now, these are not possible in the brain, but we expect that to change in the not too distant future. Dramatic progress is being made here. When it is done, it will be an irreversible therapy. And therefore, because it's also new, that will come with substantial questions about safety and regulation. So why does the path to this take time? As you've probably guessed, that word safety came up again and again and again. It is difficult to make these, especially when they are cutting edge therapies. And we have seen some notable moments where moving in these new areas has caused problems. Examples here being in haemophilia, there was a reaction to an early form of gene therapy. And then fairly recently, there were 2 fatalities given with therapies customized to one individual. Now, this is not to say that these are not directions to go in. Each one of these led to important learning points, but it is why these are not being going straight into patients. They are being done very carefully and very thoughtfully. Because as we do this, we want to make sure that none of us are ending up on this list. And also we need to think about the entire field. It's not just SCN2A, it's all of these rare disorders. There's then also the cost aspect. Bringing these to the clinic costs an enormous amount of money. A phase 1 trial just demonstrating safety is in the millions. Once you're trying to demonstrate that it actually makes a difference, that costs even more. Our hope is that with time, there will be a new regulatory framework which will be more suitable towards rare genetic variants. And this is why, as a group, we have work going on in Europe, in the United Kingdom, and then also in the US, trying to take advantage of different regulatory environments to move forward, but always with a focus on safety. We are already seeing progress here. Remember, this is a disorder which was first really characterized in 2009 or 2012. The fact that there is so much on this slide really is a big success of our advocacy and of the scientists' work. So here we're looking at the gain of function therapeutic pipeline. What we want to see is arrows extending all the way to the right, where we've got approved therapies being given in the clinic. At the moment, we have small molecules which are already going into clinical trials, some of those with a degree of specificity to SCN2A. We have ASOs in clinical trials which have been given to patients already, including some which are tailored to a specific individual. And we have lots of downstream molecules being tested. So these are small molecules which don't act specifically on SCN2A, but act more generalized on maybe seizures as a symptom. On the mixed side, we have a single ASO which has been used in an N of 1. This is fairly hot off the press that this has been given. But even there, it is encouraging that we're seeing some success there. And this is an example of an allele-specific ASO affecting just the bad copy. And then on the loss of function side, there's been progress on the science side, but so far for anything specific to SCN2A, it's not yet made it to clinic. I think it'd be fair to say this is a more difficult problem. You're trying to make something go up rather than go down, and that's fundamentally more difficult. The arrows in red represent initiatives being funded by families SCN2A. And so we can see here again that the dollars are being used and getting there to make a difference. Our hope is to see some of these move into clinical trials in the not too distant future, then of course eventually get to approval. And we also have a small molecule acting more ubiquitously being tested in autism. I'd like to end just by thinking about the future of these. So we've seen a lot of action there on the small molecules and some happening on the SCN2A specific genetics. I see immense potential in these genetic therapies. And the reason for that is, unlike any therapy which has come before, success in one directly leads to success in the next. If you take an antisense oligonucleotide which has been successful, you can simply change the sequence, the genetic sequence of it, and you have a therapy for a new disorder. This has already been achieved with reprogramming from spinal muscular atrophy to Batten's disease. The same is true for CRISPR genome editing. In the liver, success in one disorder, transthyretin amyloidosis, led directly to success in another one of hereditary angioedema through reprogramming. Everything was the same except the genetic sequence targeting it. So if we go back to my slide where we had 300 different genetic disorders, all we need is a small number of those to achieve success, and then we will know the secret of how to move here. That's not to underestimate the safety and the regulatory burden, but we could see this progress very quickly, but it all comes down to data sharing and groups working together. Which leads us back to here, to our amazing Families SCN2A group, working together, looking towards other cross disorders. And so it is with great pleasure to introduce the start of the scientific group, and thank you for listening.